Hello. Welcome to Winter 2025. Hope everybody had a wonderful break and excited about the colloquium series this term. We got lots of great speakers, including our speaker today. So it's my pleasure to introduce Christian Brodbeck. Christian got a master's degree from the University of Zurich in neuropsychology, and I wanted to read the minors. So he has a minor in English linguistics and neuroinformatics, which I think is an interesting topic. Then he did a PhD at New York University in psychology, cognition, and perception, and a postdoctoral fellowship at the University of Maryland, right? And then an assistant research professor, and he's currently an assistant professor here in computing and software in the Faculty of Engineering. And he's going to tell us today about how does the brain recognize spoken words. So everybody give Christian a warm welcome. Thank you for coming.
Thank you, and thank you for having me. When there's questions, feel free to interrupt me. I don't mind questions during the talk. So first, as we listen to speech, our ears just receive a sound wave, basically fluctuations in air pressure. But our brain is able to turn this into meaningful thoughts, and it does that with remarkable speed. And so my research, I'm primarily interested in how the brain achieves that, and looking at that in terms of what representation the brain forms of speech and what algorithm it uses to create those representations. I'm particularly interested in how that works in more naturalistic situations. So for example, when you're listening to continuous speech or listening to speech in a noisy environment. I study this primarily with MEG and EEG because those methods have the high temporal resolution. So if speech has something like 3 words per second, so you need to have the high temporal resolution in order to measure responses related to that. It's also an unobtrusive measurement, so we can study people listening to speech while they're just focusing on the speech rather than behavioral measurements where you might have to interrupt them for taking different measurements. And so for studying speech perception, I also work on methods. I'll tell you a bit about the temporal response function methodology. I know that some of you certainly know about this already. So if I start telling you things that everyone in here knows, just stop me and I'll skip ahead. But I'm assuming that some people are not familiar with it. Finally, I like to use computational models because they force us to make things explicit. And so I'm particularly interested in how computational models that we can come up with about speech perception relate to what the brain does and how we can test these models by comparing them with neural data. So to give you a brief overview, first I'll tell you a bit about the method, the background of how I relate these models to brain signals. Then I'll tell you about a first approach that we've used for a while now where we use information theoretic models. So those are basically models of incremental information processing that assume that the brain picks up information step by step and responds to the kind of incremental information content. And we can see different aspects of such a model in the brain. I will then go ahead to some more recent work where we actually try to train models to recognize speech from acoustic signals and then test whether we can learn something from these models about how humans perceive speech. So first, something about the methodological basis. So the signal I'm going to be talking about today is from MEG, so it's relatively similar to EEG for those that are more familiar with EEG in terms of the signal, but we're just measuring magnetic fields instead of electrical potentials. So if there's enough neurons that are kind of active at the same time and with electrical activity pointing in the same direction, we can measure that at the outside of the head. And so this here is showing an MEG scanner. And so if you just look at a single trial, that's kind of what the data looks like. So you can see we go from left to right, it's about 500 milliseconds. Each line reflects the measurement of one sensor. And then on the right, you get the head map of positive and negative fields. And so here at the time 0, a tone was played. But basically, what you can see in this display that there isn't much that we see here. There's a lot of ongoing activity that basically stops us from seeing the signal. Now, with MEG, we're often interested in trying to infer where the sources for this are coming from in the brain. And so for this work, I've just been using minimum norm estimates, which are basically a relatively simple linear way of mapping this activity to the brain. So you basically just get a similar looking signal, but it's now mapped on the brain instead of the sensors. But again, you can see there's not really anything specific to that tone happening there. So in order to get the signal out of this activity, we need to in some way aggregate over different data points. A classical way of doing this is to average across trials. And so say if we average across 100 trials, then we get something that looks like this, and it's a very classical auditory response. And you can also see in the source localization, the peak there comes from where you would more or less expect it to come from auditory cortex in the temporal lobe. So that's where this arrow is pointing to. So that's the classical paradigm. That paradigm kind of assumes that you are looking at different trials, and each trial looks identical, because that's the basis of averaging, because you think you have multiple measurements of the same thing. Now, however, if you look at speech, I'm showing you here the spectrogram. So that's the acoustic signal, representation of the acoustic signal of two words that we might think should be very similar. So abduct and abduction. You'd think that at least in the beginning they should be the same. They're spoken by the same person. It comes from a database of database of words. So you think it's kind of standardized. But even here you can see they look very different. So that's not, and especially in terms of the time, you can kind of see that something that happens in the first one later on happens earlier in the second one. So that's not a good basis for averaging. If we look at continuous speech, so say we want to analyze brain responses of someone just listening to someone talking, we're dealing with a very irregular signal. You can see that here illustrated. This just is the actual sound wave. So you can see the syllables are these like larger parts of the signal. And so a way that has been developed recently over the 10, 20 years or so is to analyze these kinds of responses, called speech tracking sometimes, is basically instead of the averaging, you assume that the brain response in some way tracks the stimulus with a temporal delay. So you see here, whenever there's something happens in the speech signal, a little bit later something happens in the brain. Now this has been developed based on sensory processing, so say like the acoustic envelope like you see here. But that's not the only way you can do it. If you have a model that basically tells you what's happening in the speech, so say just for illustration, we would have a model that tells us something about the speech causes this time course of brain activity. We could use that to then predict our measurements with the same method. And so that gives us a way of also comparing computational models or just models of speech processing with brain signals. Mathematically, we're treating the brain signal as the result of a convolution of a stimulus variable with a response function. That's illustrated here. So first you have a representation of stimulus on the black line. I guess there's a laser pointer here. So this is a representation of the stimulus, and this would be our predicted brain response, and this is our hypothetical response function. And so what the convolution does is basically it goes through the stimulus signal, and every time there's a non-zero value in the stimulus, it makes a copy of the response function in the response. And so in that sense, first this here you can see is actually equivalent to an event-related paradigm, right? You have an impulse in the stimulus and you get a given response. But we can do more now. We can have stimulus events of different sizes. And based on the linearity assumption convolution, we just get responses that are appropriately scaled like the stimulus. We can also have events that are spaced closer together. So we can have overlapping responses. Here, each time we just make a copy of the response function, and we get this additive overlapping response. And now if you take this further here, you can basically have a stimulus that is completely variable over time, like in this example of the acoustic envelope. And again, by applying the same method, you can get a predicted response here. Now in our actual data, we have the brain response, and we have a hypothesis about what the stimulus is. And so we just use basically a reverse correlation method that infers or like optimizes a response function to predict that response. Some of you might be, so this is just showing the same thing again. Some of you might be more familiar with the notion of a receptive field than with the notion of a response function. The idea is exactly the same. It's just you're looking at it from a different point of view. So for the response function, you look at it from the point of view of the stimulus. Something in the stimulus, I'm now lost the point here. Something in the stimulus causes a response at different latencies. With the receptive field, you're looking at it from the point of view of the response, where the response now is determined by the past of the stimulus. But mathematically, the two are equivalent. And so now the final ingredient is that we don't have just one stimulus variable. If we want to have a more complex model of what the brain's doing, we have multiple stimulus variables. Here, a simple example is a spectrogram. So instead of just having the acoustic envelope, we can basically track acoustic power at multiple frequencies. And we can use that to basically create a multivariate regression model. So now we have a response function for each frequency band, and we jointly estimate those to predict the brain response. So the brain response is the sum of the different partial responses. Physiologically, you can think of that we might have different populations of neurons that respond to different frequency bands. But with say, MEG, we don't have the spatial resolution to pull those apart. But so each of those populations makes a contribution by producing a certain amount of current. And what we're measuring is the sum of all those currents. Yeah, sometimes we call this the spectrotemporal response function because it separates this across the different frequencies. So now in an actual experiment, we have multiple predictor variables. Or let's say we have the speech that we presented. There might just be an audiobook. We have the brain response that we measured. And now we have multiple predictor variables that reflect basically hypotheses about what the brain is processing. And so now the first step is that we estimate a response function for these predictor variables to predict the brain response. Now, an advantage of looking at this is that we can then apply this response function to held out data. So we can take a piece of data that was never used for training these or for estimating these response functions, but apply this response function to new data and make a prediction on this new data. And then we can test this to see whether we can still predict the data for this held out part better than chance. That way we can basically test whether our model has any real correlation with the data beyond overfitting. Now, in the data that I'll be showing you, we very often will be interested not in the model as a whole, but we'll be interested in whether one very specific variable is contributing to the prediction if we control for other variables. We can do this here by just removing that one variable from the data, refitting the model. So now the model would just be a little smaller, and then testing whether that affects our ability to predict the held out data. So that way we can basically have a conservative test of whether this variable is represented in our brain responses when controlling for a whole set of other predictor variables. So a first step in applying this method for us was to test whether we can use this to distinguish linguistic from acoustic processing when people listen to speech. And so for this, we took a model of incremental word recognition and applied that to create predictor variables. I will first tell you about that briefly, and then we use this to answer a question, which is, do we track words in ignored speech? So when you listen to two speakers, we all have the experience that we can only attend to one. We have to decide who to attend to. But there's been a long-standing question about whether that means that we can only process words in one speaker, or whether it just means that we can only attend to words in one speaker. So basically, is there a level at the brain where words are represented even if we don't attend to them? Yeah, so we used a paradigm or general in the, yeah, and it's many experiments that we did, we just basically used audiobooks. So people have their MEG recorded while they're listening to segments from an audiobook. Now, I'm not sure if the sound is going to play. I just have a short excerpt to give you an idea.
Which, under the name of Battle Abbey, was a rich and splendid place through many a troubled year, though now it is a gray ruin. I
guess it's just coming from my laptop, so apologies if you can't hear it. But it's a simple audiobook. It's just, so it's very naturalistic, right? We first did this just with a single speaker to test our models. And then, as I mentioned, we wanted to test what happens when you have multiple speakers. How does the brain represent the signal from the two speakers, or segregate the signal from the two speakers? And so we have a second condition where we simply play two audiobooks together and did this in a way that we could counterbalance between who people attend to. So basically, we play two speakers. Half the participants attend to the male speaker, the other half attend to the female speaker. And that way we can counterbalance for any kind of inequalities in the stimulus signal while we study the attentive processing. I'm assuming you all have experience with listening to people while there is noise in the background. I'll play quickly, but probably because it comes from my laptop, it's not going to be the same experience that our subjects had, but kind of just give you an idea.
The noise being heard by a guard of Roman horse soldiers outside was mistaken for resistance on the part of the English. The guard instantly set fire to the neighboring houses, and tumult ensued, in the midst of which
So I guess you noticed you can't attend to both at the same time. It's just one. Yeah, so a model of incremental word recognition. A lot of you might be actually familiar with this if you ever had a psycholinguistics class. We started with the cohort model from Marston Wilson. The idea is that people basically start by activating multiple words and then multiple words that are consistent with partial input, and then deactivate them when they receive more evidence. This has often been studied with the visual world paradigm. So imagine the situation, so familiar with the visual world paradigm? So basically, people look at a screen while they listen to instructions, and we track their eye movements. So this would be a typical display, and imagine the instructions: pick up the beaker. Now, what do you think people will look at when the trial starts? Any ideas? What is that the first thing? So I'll show you the data. What happens is there's an early phase where people equally look at the beaker and the beetle. And then there's a later phase where people, like you said, start looking at the beaker. So the somewhat, maybe even counterintuitive finding here is that people don't wait until they hear the whole word to recognize the word. People start trying to interpret the input as soon as it starts. So basically, you hear bee, that could be beaker or beetle. And so people start kind of trying so people start looking at both possible candidates, and the underlying model says people consider both of these alternatives at that point. So how do we model this? We use a Bayesian model of word recognition here. And so for the moment, let's assume we only have 6 words in our lexicon. So at the beginning of the word, there would be a probability distribution over which word you're going to hear, right? That's just kind of how frequent that word is in the language overall. That's illustrated here with these bars are probabilities. Now, assume here, up here we have the spectrogram of the word. So the word starts, and you get a first phoneme, say F. Now, F is inconsistent with writing, so we now drop writing as a potential candidate. And then we normalize the distribution, so we have a new probability distribution over what word we're currently hearing. Then we get now we can again, we drop words that are inconsistent with, so fox doesn't start with fa, so we have to drop it and renormalize. We keep going like that until we converge on a candidate. So say this is our model. how do we connect that to brain activity? For this, we need a linking hypothesis, or what's called a linking hypothesis, which is a hypothesis about how a model is related to neural activity. And here we turn to information theory as a linking hypothesis. We have two variables that we use from there. So the first is surprisal, which basically quantifies how much new information you get in a signal. So imagine you're in a situation in which you are expecting the. So this cloud here represents a probability distribution with the being the most likely continuation, and then you actually get the. So in that case, the doesn't provide you much new information because you already predicted it was going to happen. So surprisal is low. So our prediction would be that brain activity is low. On the other hand, if what you actually hear is pause, so that's now different from your prediction, then surprisal is higher, and you would expect more brain activity. A second linking variable that we're looking at is entropy. Entropy quantifies how much uncertainty there is. So if you're in a situation where you have one candidate that is highly likely and everything else is unlikely, then your entropy is low. There's a low amount of uncertainty. And in that case, we also expect brain activity to be low. On the other hand, if you're in a situation where there are many different possibilities, so there's a lot of kind of competition between different representations, in those situations, we expect brain activity to be higher. How do we apply this? How do you apply this to our model? So first, surprisal is quantified as the incremental difference between probability distributions. So basically, the more the probability distribution changes from one step to the next, the bigger is surprisal. So you can see here where we drop a likely candidate, we have some surprisal. We drop something else that gives us some surprisal, then it stays the same for a while, there's no surprisal. And then it starts changing again, especially here where something that was very low to begin with became very large later. That's a lot of surprisal. Entropy just reflects how many different possibilities there are and basically how even the distribution is between them. So that tends to be higher in the beginning of the word when there are more possibilities and tends to go lower as you get more evidence basically about the word is. So basically we use these two linking variables now to look for brain activity. And so this is kind of how our model looks like. Our dependent variable is the MEG signal, source localized MEG signal. We first include some acoustic predictors just to control for acoustic processing. And then we have the predictor variables related to linguistic processing. So first we kind of get an intercept at word onset that should basically tell us if there's a brain signal that's specifically linked to word boundaries. For those with less speech background, one of the kind of noticeable things about speech when you're first looking at it is that there are no obvious word boundaries. So if you just look at a spectrogram like up here, you can't actually tell where the word boundaries are. So just to clarify that, this is not actually an obvious variable. And then the two variables that I just discussed. So these are basically impulses that occur at every phoneme and are scaled by the size of surprisal or entropy. So first, looking at the single speaker data, and I'll now show you two things for each of those predictor variables. On the left, you have the significance, and we're just looking at the temporal lobe here. I kind of have trouble finding my laser pointer. So on the left side, you see the significance. So that is now like the full model predictive power compared to a model that is missing just that variable. And then on the right, you see the estimated response function. So that basically tells you across time how much brain activity was predicted by that predictor. So for the acoustic variables, as expected, they're significant, and the response functions look kind of how we expect them from previous experiment with these two peaks. Interestingly, we found a strong response to word onset, so suggesting that people are actually tracking those word boundaries, even though they're not obvious in the acoustic signal. And then finally, we also find significant responses to our to information theoretic variables. So suggesting that we can find, or we can see brain activity that's related to the amount of information provided for a linguistic, interpretation. And now the important thing is we see that after controlling for the auditory responses, right? So next, we turn to our two-speaker data. And here, the kind of a way this has been described, or the question that I asked or put you before is, what happens to lexical representations in this case? So you hear two speakers talking at the same point. Does your brain at some point infer or recognize words in both talkers, or does it not? This has been formulated as a filter model quite a while ago. So basically, you look at this as an information transmission problem. So you have at an early point, all the input gets submitted to acoustic analysis. But then you have a late filter model where basically everything is analyzed lexically. So that would mean the brain looks for words in all the signals that come in. And then there's a filter at the semantic level, and that's why we can only attend to one speaker at a time. The alternative hypothesis is that the filter already happens right after the acoustic representation. So basically, only one signal can get passed on to lexical analysis, and words can only be detected in one speaker. There's been a lot of kind of circumstantial evidence for the late filter model. So one that you might have heard in an undergrad class is the Jerry's cocktail party phenomenon, that when you listen to someone and suddenly you realize someone said your name in the background. So that one way you could explain that is we're actually always listening to all words in the background, and only if those attract our attention, then we switch. But usually it's all subconscious. So, and then people have tried to study this more systematically in different ways, but I won't go into details here. But so for a general problem is that with like things like priming studies, it's hard to rule out that people occasionally switch attention, and that leads to small priming effects, or even that if you have a task that kind of draws attention to the background, that might also be a confound. So here, now, in our case, or for this, imagine we could just measure people's word recognition without actually giving them a task. They're just listening to those two speakers, they're attending to one, and there's no other task. And from their brain responses, we can see whether they're recognizing words or not. So it seems like the ideal application for that, to test that model also. So first, I'm showing you the same kind of representations again. First, we looked at acoustic responses. First one kind of interesting finding actually is that we could see acoustic representation of the unattended speaker. And now that's after controlling for the acoustic signal itself. So basically, it seems to be that people represent acoustic features of the unattended speech even after they process the mixture. I won't go into the details here, but we have a paper on this, separate paper on this. But now looking at the lexical processing. So first, for the attended speaker, we found basically something that looked very similar as for the single speaker case. So we have responses with a similar latency. They're slightly delayed, which is a common finding that brain responses get delayed in noise, but it looks similar. Now we look at the unattended speaker. And what we found here was just nothing. So it's a striking difference between those two. So, so these results suggest that at least in the case where we don't have like any switching task or any other circumstances where it's just there's two speakers and you're continually listening to one while ignoring the other, it looks like, at least in that situation, the early filter model is a more accurate representation. So people are able to turn off lexical processing at that level. On a higher level, this also suggests, it's kind of a validation of our finding that this is actually lexical processing, because you could have said like, well, maybe, so speech is, well, one of the problems with studying continuous speech, right, is that everything is correlated with everything. So people probably, when there's higher surprisal, people might say it a little louder, for example, right, because they're emphasizing more important information. But in that case, you wouldn't expect attention to affect this if it's just acoustic processing. So this, in some sense, suggests that there is actually a difference between those acoustic predictors and the linguistic predictors because they're differentially sensitive to attention. So now, I've told you about this, basically, phoneme perception on the word level. in reality, there's a long literature going back suggesting that people take into account context when they perceive words, right? So the whole N400 literature, I'm sure a lot of you are familiar with. So like based on the model I've given you before, you start hearing a word and it starts cap. You would activate captain and you would activate capital, right? But now what happens if this word appears in a context? So with damned spirits, the men stood around the grave. They mourned the loss of their cap. So it's a context that makes captain much more likely than capital. So the question is, what happens in that context? Is word perception influenced? Do we like? I'll actually show two graphs that show these possibilities. So one possibility is the word perception like module might just not care about context. It might still activate captain and capital. But then there might be a later stage where that decides based on context, captain is probably the word. So that's illustrated here where both candidates get some activation. There's another possibility, which is that capital is kind of inherently inhibited before you even get there, and that it never reaches a meaningful activation stage and only captain is activated. We can think about these in slightly different terms. So I would call this a feed-forward model, because basically the lower level is not influenced by the higher level, right? The lower level just does its lexical perception, and then the higher level takes the result of that and incorporates it into the sentence meaning. Whereas this here, I call this a unified model because the representation is unified across the layer. So here the expectations from the sentence level would feed back to the word form level to make that level consistent with our expectations from the sentence. So both of these possibilities, and I'll actually show you a third one later, and there's all some kind of evidence speaking for them. So this is a question. Say, let's take the feed-forward model. There's cross-modal priming effects suggesting that we actually do get priming for, in the previous case, capital. So contextually inappropriate candidates actually do get priming in those experiments. However, there's also some evidence suggesting that the high level can influence the lower level. So for example, the word recognition process can bias our perception of phonemes. The third possibility I wanted to discuss is that actually we might be doing both of these things at the same time. We might have one kind of module in the brain that tracks only low-level contingencies, and we might have another module that puts everything together. And there's some evidence here suggesting that this might be a hemispheric difference, actually. So there's some evidence that the left hemisphere is more like a unified model, whereas the right hemisphere is more like keeping separate representations. So how do we test this? So now we're just looking at, again, audiobook responses, but we create models for different levels of speech. So first, we create predictive models. Again, so we're now kind of expanding the surprise and entropy paradigm, but using models that predict different things rather than just words. And so here we created a model that only uses the past 4 phonemes to predict the next phoneme. So that model doesn't even know that there's word boundaries. It just is trained on a whole sequence of phonemes, predicting the next phoneme from the previous phonemes. Another model, that's the one I told you about in the last study, that's the word model. So that one knows about what's happening in the current word, and it's trying to predict what the word is, but it doesn't know about anything that came before. And finally, the kind of what we call the sentence level meaning, although it's slight exaggeration given that we just used the 5-gram model, but it uses the past 4 words to predict the next word, but then it combines that information with the information within words. So it's basically the same as the word model, but it also changes the probability distribution at the beginning of the word based on the previous 4 words. So now, if you think of this in a feed-forward kind of model, you would expect to see evidence for all these different representations, right? Because the phoneme level doesn't know about the context, so the phoneme level would only kind of use this level of prediction. On the other hand, in a unified model, you would now expect that things that the top level knows, things that the sentence level knows, they should filter back, or they should be passed back through feedback connections to the phoneme level. So now you should actually not see any effects of the lower levels, because those should be wiped out by the predictions from the higher level, right? Does that make sense? Okay, so let's look at our results. So the linking variables were again surprise and entropy, and now here I'm showing you for each of those three levels the significance when controlling for everything else. So again, we're controlling for acoustic power. For each model, we're controlling for the other models. And then so interestingly, what we found is that actually each of those models is able to explain a component of the variance of the data that is not explainable by the other models. So it actually does look like, or let's look at the different hypotheses again. So for the unified model, we would have predicted that we should only see evidence for the sentence model, but that's not the case. We see evidence for the sublexical and the word level. So it seems like there's something in the brain that treats the word as if it's starting anew and doesn't take into account the previous words. So the unified model is not a good description of the brain as a whole. Let's look at the feed-forward model. So that is the prediction we discussed for the feed-forward model, right? Feed-forward would predict that you have a lower level that's doing processing sublexical context, and then as you go up, you have higher context. However, there's an additional prediction that this model would make, and that is that the responses related to the lower level should precede the responses related to the higher levels, right? Because the signal should get passed on. Now, interestingly, that is not what we found. If you look at the response functions, we found there's an early response component which happens at the same time for each of those models. And then there seems to be more extended processing, but only at the sentence level, which makes sense because at that point you're probably then processing the meaning and things like that. But so there's an early point where it looks like the input is directly making contact with these different context representations. So that suggests evidence for a parallel processing model. So it suggests that there's different brain modules that keep track of context, but they all work with different contexts. So summarizing this briefly, so this is a model of incremental processing. It always assumes that the brain uses new information right when it arrives. And we can measure how the brain is doing this by using different models of context, right? I showed you how we can use this also to measure this in different contexts, right? So the two-talker situation, for example, where we can use this fact that we can measure lexical processing to ask how does lexical processing change when you are in a different situation. And I've shown you evidence that at least in neurotypical young adults, it looks like they're processing these different contexts in parallel. Yes, I will now switch to our newer model, kind of a newer generation or type of model, where in the previous work I showed you, we always had to kind of rely on forced aligners to and experimental knowledge to know like what phoneme happened at what time point. Ideally, we would like to just be able to use the audio and have a model that can work directly with audio. So let's think for a moment about what kind of model could even represent human perception from acoustic signals. So let's say a model should be able to read a spectrogram and it should tell you what word that is, right? So it should take as input spectrogram here and tell you this word is phantom. A very critical thing for human speech recognition is that humans are bound to move linearly in time, right? So a human perceives that acoustic signal from left to right. Now, a type of model that has been used to model human behavior like that is the recurrent neural network. So at a very basic level, the idea is your network starts with a state. I'll call this as 0 here. And then the model gets a slice of the input, a slice of the sensory data, and it combines this with its state to create a new state. I call this S1 now. It receives the next slice of the input, and again, it combines this with its previous state and creates a new state, and so forth. So that's at a very basic level, this idea of incremental sensory processing. Now, when I say computational model of speech recognition, you might think, well, Siri is able to understand me by now, so why shouldn't we just use these kind of highly advanced AI models when we look at this? There's a critical difference in that most of these systems don't actually treat time linearly. So traditionally, speech recognition models that use recurrent neural networks, they typically treated the signal like this. So they had one network that goes forward in time and another network that reads the same signal backward in time, and they combine information from the two models, and then they tell you what there was in this, like what the words were in the speech signal. Modern transformers are even more general. They just take a whole chunk of speech as an image, and they combine information backwards and forwards in time and create an output. So for that reason, those two models, they're not good models of human perception because they don't have to move through time linearly the way humans do. So recently, Jim Magnus and colleagues, they proposed to use recurrent neural networks as a model of human speech perception. And so I'll briefly describe their paradigm that they used. It will not be exactly what they did, because I'll already incorporate some adaptations we did for our project. But basically, the idea is you have the input is a speech signal. And to simplify things, we just take words that are produced by synthetic speakers so that we can create a better data set, or more feasible for creating a data set. It receives those, and it has to, the RNN moves linearly through time, and the training signal is at each time point the word that is currently being said. So you can see here, basically the output would be have the dimension of the number of words. At every time, usually when there's silence, all the outputs are 0. When there's a word, the output of that word is set to 1, and all the other words are 0. Yeah, I should have included a copy of this. So basically, the idea is asking the model to give you the word before the model could even possibly know. The idea behind that is that will create the kind of predictive behavior that we see in humans, right? So that's why we're asking the model to do something that you wouldn't ask of a normal machine learning model, because it doesn't make any sense to ask the model to do something it can't do. But this is exactly what humans seem to be trying. Right. We used LSTMs. I will not go into details. That's just the more sophisticated versions of recurrent neural networks, but the basic idea is the same. I thought I had an example. Oh, the output comes later. OK, so yeah, so now our basic question was, can a model like this, in the original study, they showed that this model has some kind of behavioral properties of behavioral data, but our question was, can a model like this also help us understand neural brain responses? So in our paradigm, we took a data set where participants listened to 1,000 words from a lexical word database. So we had MEG data of people listening to a continuous stream of words. Now we trained a neural network to be able to listen to any kind of stream of words and silence. And we trained the model on a lexicon of about 3,000 words, which were designed to mimic to include all the relevant words for the neighborhood of these of the original lexicon. Sorry, of the words that the participants listened to. So the network gets the same input that people got during the experiment, and the network just makes its predictions about what word it's currently hearing, right? So you see, whenever there's a word, it starts activating several outputs first, and then it converges on the right output, usually the right one. But now we look at the hidden unit activity. So that's basically the internal states of the network as it moves through time. And so now our hypothesis is that if the network works in any way like humans do, then we should see that these hidden units do something that's related to brain activity. And so we defined some predictor variables based on these hidden unit activity. The first one we started with was just basically magnitude of the hidden unit activities. That was just kind of the idea is whenever the network is processing information, it like starts changing its values. And those values might also be when humans activate neurons. Because humans are often very sensitive to onsets or edges, we also included a second predictor variable where we look very specifically take onsets, so like changes in the magnitude of hidden unit activity. So basically these two variables are derived from the network activity. And now we ask, can these two variables of neural network activity predict brain activity? And the answer is yes, they can. So even after controlling for the kind of acoustic representations that I've told you before, these hidden units of the neural network can improve our predictions of brain activity further. So that suggests that this model learns something, or the way it works reflects something about how human brains work as well. And then as a next step now, we asked, well, can we change something about this network to make it more or less human? And the first thing that we looked at is the output space. So the output space that I've described to you before is the one here on this side, which is basically that the output has a separate unit for each word. Now, if you're familiar with this, you might have heard of semantic vectors, which are basically lower dimensional vector spaces trained to represent semantics based on often word collocations in large data sets. And those are often treated as good models of semantics, even in psychology. And so we thought, well, maybe if we train the model to recognize words as semantic vectors, that could be more realistic than recognizing words as kind of abstract single items. So we train different networks. For one, the output is a semantic vector. For another, the output is a localist representation, so each word has just a single corresponding unit. We also have some intermediates, which are random sparse vectors, where we have basically an output space of size 300, and each word has 10 random of those active, or another one with 10 out of 900 for technical reasons. Won't go into details for the numbers. But so in general, first we just look at the word recognition rate of those models, right? So what I'm showing you is the word error rate. So the lower, the better. Basically, what you can see in this is with the lower number of hidden units, there's some variability. If you put in enough hidden units, basically all the models learn this task pretty well. They can recognize words. Now, the interesting thing comes when we look at how well those models predict neural data. So we actually so first we do actually find differences. These models differ in how well they predict neural data. And then the interesting finding was that actually the model that performs best here is the black one, is the localist model. So that's that one. And if you kind of look at the order of these, it's basically the sparser the output is, the better the model is at predicting human data. So now, why could this be? Oh, and also one thing to notice that like just the number of hidden units doesn't predict very well how much how good the model predicts brain activity. So it's not just that the more free parameters, the better it becomes. That's not the case. Yeah, so why could this be? Now, remember what I told you about since the beginning, the way humans, when humans perceive words, they, multiple representations compete, or multiple words compete for recognition. I'm showing you here kind of an abstract semantic space. Now imagine you hear val. According to this model, what you would have, and so like in this semantic space we have, so okay, yeah, you hear val. You should activate valley, value, valet, valid, because those all start with val. I've placed those in the semantic space. Now, basically in the semantic output, what do you do if you hear val? The best thing you can do is basically put your output in the middle between those, the average, right? That would be like this kind of competition. But now we have a problem because in this, and the proximities here are from the real semantic space, because this space is semantically structured, not phonologically. So in fact, now if you look at that point, there are other words that are much closer to that word, but that shouldn't be activated at this point. So basically, the semantic output space makes it impossible for this model to get this kind of competition at the output level. So now we said, yeah, so let's say maybe phonetic competition is the critical thing here. Can we find any evidence in the localist model here that this model actually developed more realistic phonetic competition? And so what we looked at is this mapping from neural network to output, because here you see if the neural network only has 512 units, but there are about 3,000 outputs, you still have a lower dimensional number here. So you still have to have some mapping or kind of a vector space here that maps these 500 outputs to 3,000 words. And so what we asked is, if this model learns kind of the phonetic structure of the data, then this mapping should reflect this. And so what we did is we looked at all the word pairs and looked at how far apart they are in this mapping. So basically, word pairs, compared word pairs so here in the example you have conserve. There's a word that shares 4 phonemes, concerned, up to a word that only shares one phoneme, car, right? So here only the first phoneme is the same and then this different. So basically, if this model develops a phonetic space, then these 2 words should be closer than these 2 words, right? And this is indeed what we found. So I'm showing you here all the word pairs ordered by how many shared phonemes there are between the 2 words. And so this space was learned by the model, right? This was, we didn't influence this at all. The model never actually knew what a phoneme was. The model learned to map acoustics to words. And yet we see this phonetic structure spontaneously merged here in the model. Just to give you a kind of a baseline, this is the same analysis done on the semantic vector. And as you would expect, shared phonemes here doesn't affect proximity, at least early on. You get some more, it gets more complex with larger, when you share a lot of phonemes, because now you get to morphology, right? If you have, say, like plurals, house or houses, those also share, they like semantically similar and they share phonemes. But at the level of 1 or 2 phonemes where it's more about phonology than about morphology, there's no slope here. So now it's 3:25. Oh.
Just some people have to go to class, so if you have to go to class, then go to class. Otherwise, keep going.
Do you want me to keep going, or should I conclude? I can do it.
Up to you.
So let me see, there's one. So there's another aspect of competition now that was interesting. So now we said, let's actually look at the model. So we looked at the static space now, but now let's actually look at the model output and see if there's phonetic competition. So now I'm showing you the output of the model basically as, so we measured the output of the model across those 3,000 speakers. We're just looking at the localist model now. And then here in this first, in this graph, what you see is the yellow, so this is averaged across all stimuli. It shows you the output as a function of whether it's a target or whether it's a word that shares 7 phonemes, 6 phonemes, and so forth with the target. And so now what you actually see here was unexpected. We see that there's actually no competition in this model, at least at the output level. It activates the target relatively early on, and that's it. This is a slightly different way of quantifying it. So here we're just looking at all the words as a function of how many competitors they have, how soon they get activated. So here every line is for a target, but the color determines how many competitors that target has. And basically what you should see here is that if a target has many competitors, it should be slower to become dominant, to become the dominant word. So now first thing we thought is, well, if we don't see competition here, maybe that's, so these are just the human speakers. So those are just the human speakers that we also used for the MEG data. So first thing we thought is maybe the model just overlearned, right? Some of these tokens were actually presented during training. So maybe the model just learned, very idiosyncratic features of those tokens. So we retrained a model where we didn't include, so we took 1,000 words and didn't, 1,000 tokens from the human speaker and didn't include them in training. So the model was trained on synthetic words, on those words spoken by synthetic speakers, but never by the human speaker. And so now you can see that the target starts a little later, but it still has a relatively little competition. So this now reflects, there's now apparently just somewhat less acoustic information, but still the model was somehow able to pick out about something about those words where it didn't have to go through the whole phonetic structure. Now comparing, this is showing the same thing, but for the synthetic talkers. So actually for the synthetic talkers, we see normal competitions like we would have expected. So you see here, or even more when they're untrained. So in the beginning, when the target gets activated, the words that share phonemes with the target also get activated. On the other hand, where we look at the activation of the target as a function of how many competitors it has, those that have a lot of competitors, they become dominant later. So how are they different? One possibility is that there's some sort of co-articulation effect or context effects that affect phonemes in ways that aren't reflected in our transcript. So, for example, it has been shown that the in cat and catalog, even though they're the same phonemes, they're still pronounced differently. And people are, in controlled experiments, people are able to pick up on that difference. And so maybe the model was able to pick up on that difference. But now we were wondering why this was. And for that, we looked at the reward back at the reward function. So the reward function for this, I haven't mentioned explicitly, was binary cross-entropy loss. That function basically means that, so the loss function is applied independently to each output. So kind of intuitively, that means you get punished very severely for activating a competitor, because activating one competitor, basically you get as much punishment as for activating the right word. So in some way, this model just really encourages the model to find the right target as soon as possible. Another way of thinking about it is, so formally you can minimize this loss if you're in a situation that's probabilistic. You can minimize that loss by predicting, by setting each output to its probability. So that is consistent with models of Bayesian perception, where you basically should be able to tell the probability of each stimulus given the input you've received so far. But there's a question of whether that's also the appropriate way of modeling this in a model. Should be a model of neural representation. So like, say if we have several lexical representations in our brain, do we actually only activate each of those representations with the amount of neural activity consistent with its probability? This might be less likely. I think it's more likely, and in fact we see entropy effects, right? Suggesting that when there's more uncertainty, we actually have more brain activity. So now we try to modify the loss function in a way that takes those considerations into account. And so what we did is we said, so early on in the word, we don't want to punish the model for activating competitors. And so we introduced a loss function that differs early during words, whereas we left it the same for later parts of the word. So basically early on in the word, we simply divided we simply divided the loss, we divided the punishment you get for activating competitors. So you still get rewarded for activating the target, but you don't get punished as much for activating competitors. And we divided it by constant to be able to control the amount of relaxation of this criterion. So the idea is basically early on, when you're hearing a word, like humans, the model should be able to consider different alternatives, but then towards the end of the word, it should be forced to converge on the target. So now we first, going back to these graphs for the different parameters, you can see it had the intended effect. So here, and kind of the sweet spot was around this value for C, where you see early on the model activates competitors and then it deactivates them and keeps the target active. Similarly, you now see this, and this is now for the human talkers that the model even was trained on. So there's the kind of overfitting effect went away. You see the gradation between different environments. Once we get down here, you see this dotted line here. So that's basically when the model starts activating words that don't actually share any acoustic structures. That's kind of where we've relaxed the criterion too much. Right now, the model just activates everything. That's why I'm calling this here the sweet spot. And now, interestingly, if we look at, so first model performance, this actually improved performance of the model. So I kind of skipped over this. We trained models with different numbers of layers. That's less theoretically interesting, but like 3 layers was generally kind of the best model. But you see, the lowest error overall was for this model around this parameter. So suggesting that if we allow the model to explore the lexical space more fully early on, that actually leads to better perception. And in addition to that, this same model was also the model that was best at predicting neural data. So not only did the model get better word recognition, it also became a better model of human brain activity. So summarizing this, first, we found that activity in the neural network was a predictor of brain activity, which, and that's after controlling for acoustic activity. So that by itself was an interesting finding, not obvious. But then more interestingly, changing the architecture of this model and things like the training procedure changed the amount of predictive power of this model. So that suggests it's not just that kind of any model that learns speech processing will also resemble a brain. It actually suggests models that are designed to be more like humans also become to show activity that's more like humans. Yeah, so I've shown you first This was the case for an output space. So an output space that allows more realistic lexical competition also led to a model that has more brain-like activity. And second, if we change the reward function to be more consistent with this human word perception, that also increased the similarity to brain responses. So I'm kind of one kind of concern with models like this is that in the end, are those models still black boxes? So even though we now trained the model ourselves, do we actually know what's going on in the model when it solves this task? And I think this is certainly a concern still, but I think that this is something we can work on here with these models. And first, we can study what the models do, and the example I showed you here is we could actually look at what the model was, how the model was recognizing words over time, right? We could study cohort competition, how it happens in the model. And we can study the sensitivity of this analysis to meta parameters. So we're now basically studying what kinds of parameters affect speech processing in a way that's consistent with human behavior or not. So the example of the loss function here, what kind of constrains human speech perception? Yeah, and there's a final point which I've kind of skipped over the selection of LSTMs here, but there's actually an argument that LSTMs replicate in some ways cortical microcircuits. And I think this is something very interesting to explore further regarding different kinds of microarchitectures in models and how they relate to cortical microcircuits. So kind of stepping out now a bit, the models I've told you about, they have different, they all work with different linking hypotheses. So first, a very simple linking hypothesis that we just look for basically brain responses that correlate with the features. So that's a kind of simple acoustic example here where we basically say the more sound there is, the more the brain responds. There's some other work that looks at things like, say, phonetic features, saying should the brain respond when there's a phonetic feature present or not. I've told you about a different class of models where we look at information theory. So here we have a more complex probabilistic model of perception, and we have a linking hypothesis is the amount of information that's received and the kind of uncertainty in predictive processes. And now, where does the last model I showed you, where does that fit in? Here, the linking hypothesis is actually that, in some sense, when there's more activity in this neural network, this artificial neural network, then there's more activity in the brain. I think this is something that's interesting to develop further, because in some ways, if this model actually implements what the brain implements, this model should eventually be able to explain all the other linking hypotheses, right? It's basically, for example, the complex effects I told you about if you look at surprise and entropy with different levels interacting, eventually we should be able to implement a computational model based on neural networks that shows the same behavior, or that would be an end goal if we want to develop valid models of speech perception. Okay, yeah, I want to acknowledge all my collaborators who contributed to this work. I skipped one, but yeah, I'll be available for questions. Okay.
Christian, that is one of the most complex and sophisticated presentations that I've seen in a long time. It's amazing work. I think it's a really interesting model to learn more about the neural functions of uses collaborative cognition with AI within human-AI interactions. There are some alarm bells, some scary alarm bells that are kind of ringing in my mind right now. Is this research strictly going to remain directed at the purpose of understanding the neural pathways that process language, or are you conceiving this as something that could be integrated in AI processes within the broader public sphere?
I have no plans on integrating this with AI. Do you have ideas?
The example that comes to mind would be the Stilwell and Krasinski research at Stanford, it's associated with Stanford, but it's at University of Cambridge, where they were using psychometrics to understand whether they could predict people's personality based on online activity. So the research wasn't meant to be used to predict people's behaviors and activities online in order to exploit them at all. But then it was appropriated, and I guess ethically, I look at this research as wonderful. Like it's really broadening our understanding of how the brain works with language, and that's phenomenal. But do you ever worry about that?
Oh, I see. So I don't, but maybe I should. But I think one thing. So I think where you're going is like mind reading. Is that no? Because so one thing that there is that I'm just thinking you need a lot more data to do this kind of analysis. So you won't be able to draw conclusions for like an individual human being in an individual sentence. You're always analyzing a large chunk of data, and so you can kind of draw conclusions about that as a whole. But if you wanted to say like get into specific contents of the speech, I'm not sure that, or I don't see the application yet.
But conceivably, the model that you're exploring, it is a computational model, right?
So the second, yeah.
So if you're able to integrate that model to predict human